So I'm going to write on the board. Let's have this one down. How does this work? No, that's the wrong one. I see, that's the front one. Right. Okay, so rough outline of the talk is firstly there's an introduction, and this is where the physics is. So it's sort of hand-wavy bit. And then I want to talk about finite spectral triples, which is the main subject of my talk. And I want to reformulate a bit. And slightly generalize in some ways that are suitable, but not that different. Then I want to talk about the diagrams. And firstly, I'll talk about ribbons. And then if I get time, I'll mention briefly a slightly different way of doing it using bimodules. So that you can actually rephrase it all in a suitable bimodule category. And then finally, it'll probably be more rushed, I want to talk about defects in topological quantum field theory. Okay, so that's about it. Okay, so firstly the introduction. So finite spectral triples, that means the dimension of the Hilbert space is less than infinity. And what I'm going to say is sort of part of a project to investigate the use of these spectral triples. And the sort of things we want to do is to approximate a manifold, say a compact manifold. And we want to use them in a quantum or a random sense. So we want to look at quantum or possibly random noncommutative geometries. And by using finite spectral triples, it makes the whole thing tractable. In fact, we already have some results where we've done this, defined some models, we've even investigated them on a computer numerically, and so on. But I'm not going to talk about that today. But sort of getting towards what I want to talk about is if you think about Feynman diagrams. And again, this is a sketch because I don't really want to develop the theory of Feynman diagrams here. But let's suppose that we're doing something like this, and I write a fermion action. This is a typical sort of thing you might want to write. And you integrate over the fermion fields, and I guess this. So D naught is the fixed. This is the fixed vacuum, if you like. Theta here is the fluctuation. So eventually you're going to integrate over fluctuations here. And I guess you'll have some action for the fluctuations. And if you think about turning this into Feynman diagrams, I'm just going to concentrate on the fermion part here. You would, a typical Feynman diagram. Whoops. No, I have to wait. You'll get out of this. Well, there'll be a term here with psi, d naught psi. That's the sort of propagator thing. And there's an interaction. Well, there are two interaction terms. So the interaction term like this. You would draw like this, some sort of diagram. And the other interaction term, like this, it turns out, you see, the way to think about this is that this sort of acts on the left, and this thing here, because J flips left to right, this acts on the right. So you would end up drawing a diagram like this, where this thing has acted here like this, perhaps. And because psi is the fermion field, you also have a crossing here, and this is take two fields, two fermion fields, and you'll get minus the flip of the two on the top there. So you should read these as linear maps going from here to here. So this is, takes, in fact, think of the tensor product of these here to this number here, and likewise here. So I'm often going to leave out the tensor product on the bottom here, but that's implicit. So the tensor of those two goes to the tensor of those two. And in this Feynman calculus, then you would use the propagator term you would then be the other way up. It'd be like this. So this is D naught, if you like. And this lives in the Hilbert space. This is some element in H tensor, H conjugate, something like that. And your Feynman calculus game is to glue all these together. So you expand this exponential. You have lots of these things here, and then lots of these, and then you glue them all in all possible ways, and you get some diagram. And so some observations. Firstly, because it's non-commutative, the order in which these things arrive at a vertex matters, and so you have to think of this as really different to that. And in fact, it seems to be a good calculus to think of these lines really as ribbons. So actually, you actually sort of get a ribbon structure like this. So you should really think of these sort of geometrically like this. And it turns out that this complex conjugation here, where you have psi bar, you should really think of physically flipping the fermion upside down, as it were. So you should put in. You should twist the ribbon over like that to indicate the conjugation operation. That's how that works. And so what I'm going to talk about in the rest of the talk is sort of a systematic way of getting these diagrams like this for a non-commutative geometry.
Why is there a minus psi prime on top there in the vertex?
Minus?
Yeah.
Because these are fermions. You remember if you have fermions, there's a minus sign when they swap over. So that would come from this, being a Grassmann integration and not ordinary integration. And what we learn it goes that way. Now I have to wait. So what we learn from doing this is that the non-commutative geometry axioms become geometric relations on the diagrams. And I've, when you do this right, it is both ways. In fact, you can start with the non-commutative geometry axioms and derive a bunch of relations on these diagrams here, and you can do it the other way around. If you have these diagrams with a bunch of relations, you get all the non-commutative geometry axioms. So it really goes both ways. And that leads, once you've done this, you then leads you to a way of thinking about non-commutative geometry axiomatically in a diagram category. And so you can generalize this to give something like a non-commutative geometry in a blah blah monoidal category. Where you insert your favorite blah here, whether it's pivotal, spherical, symmetric, monoidal two category, or whatever. So anyway, something like that. or braided or something. So you could have braided non-commutative geometries. So it depends, just what you want to do and how you want to generalize this. So what I'm going to do is more or less describe the original non-commutative geometry, what you get in diagram world, and then as homework you can do all the generalizations yourself.
Do you know what blah would be for the standard model?
Yeah, so if I get to this bimodule thing, it's in a symmetric monoidal 2 category of bimodules. Okay, so I guess that's the introduction. So that goes up, yes. Yes. So some of what I'm going to say will survive in the infinite dimensional context, of course. And it's much like you first study representation theory of compact Lie groups. And then when you've done that, you study representation theory of non-compact Lie groups. And you recognize that if you look at it in the right way, suitable things survive if you, treat all the parameters as living in the measure space and all this stuff. So your second homework is to generalize this to infinite dimensional setting.
Commutativity is related to the quantum physics.
I guess so, yeah. So, okay, so two finite spectral triples. And I'm going to ignore chirality. Just to keep it short, the chirality operator will be in the paper. So a whole sequence of various remarks generalizing or reformulating the usual notion into a form that's suitable for the diagram category. So the first thing I'm going to say is that every vector space is complex. Vector space is complex. So, for example, you have a real algebra actually when you formulate the standard model, for example. So I'm just going to tensor that with complex numbers and call that the algebra. And similarly for other spaces that appear. I'm going to think of A as a Frobenius algebra. So what does that mean? It means it has a non-degenerate associative form. So there's a that's a bilinear form. And it's associative. And it's non-degenerate, which you can formulate the following way. You can say that there exists a B, the inverse gadget in A tensor A. And you write this as sum of B1. Somebody can't see, I'm guessing. Yep. You can't see, yes. So it's that one, and that goes up, and then it will disappear. Isn't that handy? Right, so you can formulate it like this, and that means that, and then you have equations like like that. So it's the inverse matrix, if you like. And some other conditions on this algebra. It's going to be, well, we're going to make it really, really boring. I'm going to say it's symmetric, and it's star compatible with the star. Like that. And there's another condition which plays an important role, which is it's what's known as special. And I guess still people can't see. So special is that if I multiply B1 with B2 and sum, then I just get the identity element in the algebra. Anyway, all this is pretty restrictive, and it implies that A is semi-simple. So it's just the direct sum of matrix algebras.
Doesn't this imply that A is also finely dimensional?
Yeah, so everything's finite dimensional, yeah. Right, so what do I want to say? Yep, so I still want to use this board, so I want to come... No, I want to come back down. Yep, okay. And the actions of A and H are not required to be faithful. Not necessarily faithful. So normally you say the action is faithful, but I'm not going to. So I've got a left action, which I'm also going to write. I'm going to use this notation. And there's a right action. So U is a typical element in the Hilbert space. Well, I say Hilbert space, but the next point is that H has a non-degenerate Hermitian form. Hermitian form. But I'm not going to require this to be positive definite. Not necessarily positive definite. So that's a fairly big generalization, but it includes the Lorentzian examples that people were discussing earlier today. And in fact, the condition that is positive definite is somewhat unnatural, and that's the reason why. I mean, so to express the fact that it's positive definite, you'd have to say something like this. But the problem is there's no operation that takes an element U and doubles it and gives you U tensor U. There's no linear operation that does that in this theory. So even writing this condition here is just completely unnatural. So let's just scrap it. Okay. So when I say Hilbert space, you have to take.
You have to define this Hermitian structure. Like you say there is an Hermitian structure, so you can choose any one you want.
Yeah.
You want to say there is not a natural dual space.
Well, everything's finite dimensional, so there's a natural dual space. Yeah. So it's non-degenerate, so nothing bad happens. And then we're going to define the bilinear. Inner product. Like this. So J is the real structure for my my real spectral triple. It's a real spectral triple. May have forgotten to say that. So finite real spectral triple. And so this gadget now, this is antilinear, and this is antilinear in the slots. This thing here is now bilinear. And eta here is a complex number, which is a 4 through to 1, which we'll pick a bit later. And I want to reformulate the axioms in terms of the bilinear and not the Hermitian thing. And that turns out to be convenient. But yeah, you can swap from one to the other. You can obviously write one in terms of the other backwards and forwards. So it's just a rewriting, basically. And now the unitarity of J, which we discussed earlier this afternoon, is the following form, that the Hermitian product of Ju and Jv is plus or minus this thing here, Vu. So normally in a positive definite situation you would just write a plus sign, but in fact we can have plus or minus, so there's a sign coming on here. So you choose plus or minus 1 here. So in fact in the positive definite situation you can pick u equals v, and then this is positive and this is positive, so obviously phi has to be 1. But when you're not positive definite anymore, then it can be minus 1, and that happens. In fact, that got discussed earlier today as well.
Can I just pause for a second? So
Yeah.
When you said H, so when H has a non-degenerate Hermitian form, and that was a generalization that included the Lorentzian case that we
Yeah.
discussed earlier, what's the generalization about it? That there's nothing about the completeness of the, there's nothing.
It's just not positive definite. That's all.
There's enough people.
Okay. So, right, and then we want to translate this condition into the bilinear form thing here. So it's that one, and I go like that. Yes. And so that translates as follows. This condition becomes the bilinear of u and v is phi times v j squared u. That's what you get if you just substitute in this definition here. You can just check for yourself. And of course j squared is n plus or minus 1. So you can also rewrite this as phi epsilon vu. And this thing here is plus or minus 1. So the sign of this product here will tell you whether this bilinear form is symmetric or antisymmetric. So this is symmetric or antisymmetric, as phi epsilon is plus or minus 1. So just a reminder, j squared is epsilon. In actual fact, I want to not go to an eigenvalue of j squared. I want to think of j squared as an operator. That's just sort of convenience. So in fact, I'm going to say that j squared is an operator. And I'm going to, but I'm going to say that j fourth is 1 for definite. So it only has eigenvalues plus or minus 1. And to make sure that this generalization is boring, I'm going to make sure this commutes with the action of the algebra. So this generalization doesn't really do much, because you can just split the nearly Hilbert space up into two parts, the eigenvalues of j squared, and so you've just got two spectral triples. But you see, it means I don't have to mention the sign of j squared anywhere. I can just say j squared, and it can have either sign. Okay. Now I need a little bit more somewhere. Yeah, I guess I can just go on the bottom here. That's okay. I need to move this up, which means going... No. Ag. That one means going that way, yes. And the next ingredient, or the final ingredient, is there's a decomposition. You can always write D as an operator plus... And again, this is special to finite dimensions. There's a decomposition like this. where theta is maps the Hilbert space to itself, and it commutes with the right action. And of course it means that this gadget here, J theta J inverse, commutes with the left action. So it's just splitting the Dirac into these two pieces. But it's much simpler to work with theta and not with D. And in fact, so this condition here on its own, this implies the first order axiom for D. Okay. So if I do this double commutator thing with D, then one part commutes with this and the other part commutes with the other bit. So, yeah. Okay, so that's that. So this goes up. This comes down. So I'm ready to do part 3, which is the diagrams. So diagrams. So there's a bit of preamble before I start drawing some diagrams. So I just want to mention some notation. I think I'll mention it over here and then I can rub it out later. So if phi is antilinear, then I want to regard this as a linear map from V to, and I'm going to use the same notation, so that's linear. And W bar here means the complex conjugate vector space. And also if I have a linear map, so big psi, then there's associated to that a map from V bar to W bar. And in fact, you just take the same map of the same underlying set here, the same map is also a linear map, so I'm going to use the same notation for that. So of course it means that you know phi also maps in this example here V bar to W in the same way. So okay, so I'm going to use that same notation. And this turned out to be not just a notational device, but actually there's an important point here, which is that complex conjugation is in a sense a symmetry. So it turns out to be orientation reversal symmetry. Orientation reversal symmetry. And that's actually sort of the key to understanding the real structure in the noncommutative geometry. So, for example, if I start with H, then I can make H bar the complex conjugate of the nearly Hilbert space. Then that is an A bar bimodule. And you use the same map, so you use the left action, but now regarded as A bar tensor H bar to H bar. and the right action. Okay, so these are the same as for H. And I write the exclamation mark there because you might, if you came to this fresh, try and write something different down, and then nothing works. So this, the fact that it is these, making it this bimodule is an important part of the story. So it's sort of, it's like, you know, so physics in this room happens with various linear maps, but if I change the orientation of this room, you wouldn't notice. You carry on using all the same linear maps in all the complex conjugate vector spaces. And the only thing that would be different is that all the complex numbers you meet will get complex conjugated. So if you have a detector that can detect the difference between a complex number and its conjugate, you would notice, but otherwise you wouldn't notice a thing. That's... I don't know, orientation reversal. Maybe, parity. I just mean, you know, if you change the if you're on an oriented manifold and you do something and you change the orientation to the opposite orientation.
The manifold in question are your ribbon diagrams? Is that what you?
Yeah, I'm going to have diagrams. Yeah, exactly. I'm talking about my diagrams.
I don't think it's quite space-time orientation.
Well, space, no, diagram space, whatever. Yes. Yeah.
You wrote a diagram.
Exactly. Yes. Exactly. Yes, that's it. Yes, it's that space. Oh, and you'll see that in a minute. Okay, so let's start out with some diagrams. So I'm just going to draw some and then explain what I'm doing. My usual sin is not to leave enough space. Okay, so this is a ribbon picture for, these are algebra elements here. So you should think of this as a map from tensor A to A at the top. So one ribbon is one instance of the algebra A. And I've written here a typical element of this space, and as I said, I'm missing out the tensor product symbols. And when these two lines meet, you multiply them, of course, and when these meet here, you multiply them. So this is AB times C. And then you can draw a similar thing, but with this one smaller and this one bigger. And you decorate the same things on the outside. And of course here now you multiply B and C first, and then you multiply by A. Okay, so you travel up the diagram, and then you do things as you meet the interactions, as it were. And the point is these are equal, and that says the algebra is associative, and now we've coded that into the diagrammatic language. Okay, and similarly, you get the hang of this quite soon. So this thing here is the identity element in the group in the algebra. So this here means multiply on the left with E, and that's this thing here. And obviously you multiply on the right, the same thing. So this was axiom number 1. Number 2. Actually, maybe I should go across and then I won't have to move the board so much. Yeah, let's go across. Okay, so the star in the algebra is a twist where I twist the ribbon here. And now star is 1, so it doesn't matter which way I twist it, so I don't need to record that. So in fact, let's write that explicitly. This is A star, and that equals, obviously, the identity thing, like that. And then I can write other axioms like this. Multiply and then star them, and then I can do it the other way, which is like this. careful with. So here I star A and B, and then I flip them over, and then they get multiplied. So this is B star A star. And already something should be apparent from these pictures, in that all these relations are what you get from just moving the diagram around in space. So these things here, all I do is just go like that to get this one. This here, I just push it. And this thing here, I just flip it over. And the same is true here. This thing here, you flip that over, and then you see that picture there.
John, how do you add, since it's an algebra, how do you add elements?
Oh, that's a good question. No, everything's linear, so all the diagrams. So, this is a vector space, so I don't need. That's not diagrammatic. It happens in the category of vector spaces, if you like. Okay, that was axiom 2. Axiom 3, now let's get something more interesting. So this is, let's draw this one. I'll draw the picture first. So this is where we first meet the Hilbert space. And I want to distinguish the Hilbert space from the algebra. So I'm going to put a dotted line along here. So when you see a ribbon with a dotted line down the middle, that means that things live in the Hilbert space. So I'm going to put U and V here. So they live in H tensor, what do I mean? H tensor, actually I have to put this here. Well, that's in H, and this is in H. No, that's in H dual, and that's in H. That's the way it works. And now this flip here is the J operation, as you might have guessed. So by the time I get up here, I've got U tensor JV. And then when I get up the top, this thing here is the inner product. It's the bilinear inner product. And because by now we're in H bar, tensor H bar, the bilinear inner product goes to C bar. And then, of course, to get back to C, I have to complex conjugate everything. So the final result up here is the bilinear inner product of U, JV, complex conjugated. And what this should equal is the same thing on the other side. U and V, and this is J, U, V. So I hope that's something I wrote down already. I meant to if I didn't. It's that one. Did I write that down? Perhaps I didn't write. Okay, well it is. Should have written that down. Yeah. Okay. So if you translate this back into the should have that in my notes somewhere. Where's it gone? Yeah, I may have gone too fast here. Maybe some calculation to do, yeah. So let's do the calculation underneath somewhere. Okay, so you start with, no, do it here. This is the standard axiom in. It says the inner product is Hermitian. And when I turn that into the bilinear product, I get the following thing. like this. And then when you can use this relation here to flip that around and get phi epsilon ju v times eta squared. Whoops. Okay, and we see the diagrams are forcing us to have these two things equal, but my calculation reveals that there's this sign factor here, this product of them all. And so we want these to be equal, so we set the sign factor to be 1. So if you like, that defines eta squared. So let's write that more suggestively. See, eta was free up to now. I just said it had to. I just said that eta is some complex number. Its fourth power is 1, so this is just some sign, and so this is what the sign has to be now. And now these diagrams are equal, and you can see what it is. It's just that if you take this half twist here and you push it round the corner, then it turns into that half twist. So so that what you should do is dictated by the geometry of the pictures. Okay, so that's number 3. Geez, lost my notes now. That's where I am. Yeah, that will come. So the next axiom, number 4, is the following thing. And this tells you that, no, wrong one. It's that one, yes. Remember, this thing here is the bilinear form, so this is the inverse of the bilinear form, and this is saying that the thing is non-degenerate, it has an inverse. And that's just the equation that says the thing times the inverse is it. So it's just like for the Frobenius algebra, which I explained before, there's exactly the same thing for the space H. And obviously, same relation on the other side. We just flip that over. Okay, so relation number 5 is the action. So this is like the associativity, except that I have a main road here with a line down the middle. So this is A and B acting on U. This is in the algebra. This is in the algebra. This is in the Hilbert space. So this is A times B acting on U, and obviously that has to be equal to that, which is A, B, U. And a similar diagram on the right-hand side for the right action, obviously. And there's an analogue of the identity thing. Obviously, there's a diagram like this that says that the action of the identity is the identity. And then 6 is similar. This is called the snake, by the way. So there's a snake for A. So just draw the same diagram without the dotted lines in it. There's some more relations. For example, the associativity of the Frobenius form here is like this. So this is the associativity A, B, C equals A, B, C. And there's more. To express all the other axioms I had for A, I won't bother drawing all the diagrams, but I think you get the idea now. But there is one I should mention, which is very important, which I'm going to rub this out and do it here. Which is, remember the special condition that's up there, that if I take the inverse gadget and multiply them, I get the identity element in the algebra. So that is this condition here. Okay, so remember this thing here, up to that level is B in A tensor A. This says multiply the 2 bits of B. So up here I have sum of B1 times B2. And this is the identity element here. So that equation is the thing that says it's a special Frobenius algebra. And this axiom actually is rather different from all the others in that so all the others are to do with deformation. I can just move things around. But this one here says I can fill in a disk here. I can glue in a disk for free. And that's the key to making a surface. That's how the whole two-dimensional TQFT thing works. You end up with all these ribbons, but actually whenever you have a circle boundary, you can fill in stuff in. And let's keep going. 7. There's a similar diagram to this, but with a Hilbert space, or nearly Hilbert space. So like this. No, I haven't left enough room. So let's read this. So these are elements of the Hilbert space. This is an algebra element. So up here I get the bilinear inner product of U with A acting on the left with V. And up here I get, this is the bilinear inner product with A acting on the right. So perhaps somebody can tell me what usual axiom of the spectral triple game that this corresponds to. Well, okay. So what it is, it's the axiom that says that A star in the Hilbert space in the Hermitian inner product language is this, that A star really is the adjoint. So when you translate that into the bilinear forms, you get this thing here. And you'll notice straight away that if you tried to draw this as a diagram, you wouldn't get very far, because A here is acting sort of on the inside of this stuff, and A star here is acting kind of on the outside. Whereas this one here, you see, because there's an extra J when you go up to here, this thing has to pass through the J, which flips left to right, you see. So that's exactly how this works and why that turns into a good diagram. How am I doing for time?
We've got 7 minutes.
7, okay, right. So there's more axioms like J to the 4th is... that one. J to the 4th is 1. It's a very nice axiom. So that is, you take a major road and you put in 4 twists. j fourth u, and that's that thing. So that's equal. And the next axiom is even nicer. It's this one here. It's the one I did spend some time on up earlier, but let me draw it now. It's quite an important one. Ah, geez. So what is this? This is the bilinear of u and v in the Hilbert space is equal to the bilinear of, this is uv. So you flip u and v over, you put in the sign, some sign here for flipping them over, and then you put v j squared u on the other side. So this is two twists here. And then we compare with the other board. Nah, done this wrong. And I already wrote that on the board. It's this one here. So we learn that that sign is actually phi. So phi is the thing that told you whether you were j was unitary or anti-unitary, and that's important and comes in. Comes in here. So in fact, this is phi. So it tells you the category is symmetric, but this flip map here is -1, the physical case, if in the anti-unitary case, and it's +1, trivially braided in the other case. And there's a load more axioms which I'm going to stop here because I'll run out of time. Well, not too many more. There's the... Well, okay, so homework to do the rest of the axioms. So you can draw, for example, the axiom that says that J intertwines left and right. You can draw as pictures. You can do that as an exercise and then convince yourself that, again, just like all the other diagrams, you can pick the diagram up and turn it around, and you see one side turns into the other side. Okay, that's basically it for the diagrams. So what do I want to say to wrap up? I promised I'd say something about bimodules. So for a long time I wondered about how to formulate this in terms of bimodules. You see, this thing is a bimodule here. This is an AA bimodule, and well, let's go to this one. This is an AA bimodule. This is an AA bimodule, and you're in a product up here, and you're in C, but C isn't an AA bimodule. So you can't regard this as a computation in AA bimodules. That makes no sense. So what you have to do is instead use a different product. So you can think of this as the inner product on H as, in fact, a more primitive product, because there's a product which goes to the algebra. Something up here. Well, what is this thing up here? Well, it's what I call the elephant diagram. You use your inner product, but you then do this. So what is this? This is this is the inner product of U with B1, B, B2. And that's in the algebra. So if you think of it that way, then this is a bimodule map. And the only thing left to understand is what happens when I put the little hat on the top. How does that work? And so what you should think of is really you should think of this in terms of a nice three category. Did I say that? Or a monoidal two category. So what I want to say. So the main thing is you can think of a fold like this. So in this, so in fact it's a grey category. And the one morphisms are algebras. So the one morph or algebras, and the two morphisms are bimodules, and the three morphisms are bimodule maps. So so this fold here, so you label this with an algebra A, and you label the backplate there with the algebra A bar, and what goes on the fold here is the trivial bimodule. You think of A as a, so this is a left, so this is an A tensor A bar C bimodule. And so what's going on here is so you act. So if you have elements in here, so A and B, and you have some element in here, then the action is A tensor B acting on C is A C B star. So you see, because of the star, it's a right action, but it's also living in the complex conjugate vector space. So that's a nice bimodule. And this thing sort of turns around. So yeah, so you can now, your J map here is your Hilbert space runs along a line here, and then out the back here, and so this thing here is H bar, and that's correctly an A bar bimodule, you see, whereas this thing here is an AA bimodule, and this morphism here is J. And what's happening at the top, which I only vaguely have time to describe, is that two of these folds are coming to meet. They're sort of getting closer together, and they're meeting up the top, and that's exactly where the inner product the final the final, you see, so that's the morphism that takes you from this A tensor A bar C bimodule on this side, and this is a C A tensor A bar bimodule, and then that maps you to the C tensor C bimodule up the top there, which is the scalars. Ha! So that's exactly where this final thing is that goes on the top there. So that was a bit vague and cryptic. So section 4 is what's this got to do with TQFT? Well, the whole point is you can now think of all this as just lines moving around on a surface. And if you follow the rules of topological quantum field theory, you could start from that point of view, and you'd write down the same diagrams here as being, these are all the topological diagrams belonging to this category here, and you'd write down all the same diagrams and come backwards back to noncommutative geometry. So that's where I'm going to stop.
Because it's the last talk, I think we have some time for questions.
basically sort of the structural two-dimensional topological quantum field theory with some extra data on that, right?
Yeah.
So would there be some kind of, say, spectral interpretation also for the higher topological quantum field theories? Does this even make sense to consider?
In higher dimensions?
Yeah.
No, I'd really love to know the answer to that. That's a very good question.
Because, I mean, three dimensions, for example, would be more related to, say, quantum groups. And then, say, since you started with Feynman diagrams on, say, ordinary space, space-time, whatever, would this be considered, for example, like quantum field theory on quantum groups and whatever?
Well, since you mentioned it, I mean, this calculus here is now becoming three-dimensional. In fact, this calculus here is really three-dimensional because you have to think of these relations as moving things in three-dimensional space. But actually, there's one relation. So if you combine this with this, you see that this relation boils down to the following. It boils down to this. With a dotted line down the middle. And this relation is, well, in three dimensions, it's true if you worry about whether you have over or under crossing. So if you get that right, then in three dimensions you just go like that and undo it. But I'm assuming in my theory that these crossings pass through each other. Over and under crossing are equal. So I can do that. So that works. But that's an unnatural assumption in three dimensions because things don't pass through each other in three dimensions, but they do in four. So if you do all this in four dimensions, then everything's fine, and this is a natural relation. And so this is, in a sense, a four-dimensional calculus. But how that answers your question, I'm not really quite sure.
Thomas, I have a question. For ribbon graphs on ribbon surfaces, we have a corresponding matrix model of integers.
Yeah.
Can you see some matrix model?
Yeah. The thing I started with, I rubbed it out now, but that was a matrix model. Yeah, sure. So everything in it had.
For finished algebra, but where are these matrices?
So I wrote down an action which had fermions, fields, and a Dirac operator. Well, the Dirac is a matrix, maps H to H, and the fermions you can think of as matrices as well. So they're.
I cannot see these asymptotics if you increase the size of matrices.
Well, now you're asking a good question. So that's a whole other talk. So in fact, I'm going to give that in Vienna on Tuesday. So if you want to come.
Last question or comment? How would the Dirac operator come into play here?
Yeah, I actually forgot those diagrams. I sort of said and there's more, but I forgot. But well, no, it's quite. There's not much to say, but the theta is another defect line in this diagrammatic calculus. So I draw that as a wiggly thing like that, and then that acts on the Hilbert space like this. So that's an element of the Hilbert space, and then up here we have theta times u. And then the axiom it obeyed was that it commutes with the right multiplication. But that's kind of almost obvious now, because if I right multiply by something here, I can slide that up and down past this multiplication here, and it's obviously true in the diagrams. So yeah, so the whole Dirac thing is just coded in these pieces here. These are the fundamental pieces, not the actual Dirac.
And is that the same true if you hit, I guess the same if you hit it with a theta from the right?
Yeah, that's right. So theta on the right is j, theta j inverse, and that commutes to the left action. Yeah, sure.